Maths of the Traitors, the final part. One of the brilliant mechanics that shifts the playstyle entirely in the Traitors is the final round tables. They no longer get updated information revealed when someone is eliminated and have to choose to either keep eliminating or decide to split the money. If a single traitor gets through, then they win the whole lot and the faithfuls walk away with nothing. In other series outside of the UK though, multiple traitors getting through to the finale has seen them navigate something vaguely resembling the classic prisoner's dilemma. They even dubbed it the traitor's dilemma. The classic prisoner's dilemma. Two prisoners are told that they are sentenced to a year in prison unless they turn on each other. If only one prisoner speaks out and betrays their partner, they get to go free, while the prisoner they betrayed gets an updated sentence to 3 years. However, if they both speak, they both get imprisoned for 2 years. Without discussion, they must choose whether to keep quiet or betray their co-conspirator. Let's look at this from the perspective of prisoner A. If prisoner B keeps quiet, then betraying them will reduce their own sentence from 1 year to freedom. But if you are betrayed by B, then also betraying reduces your sentence from 3 years to 2 years. No matter what B does, the choice to betray will always lessen A's sentence, and the same is true for B since this dilemma is symmetric. This means both prisoners betraying is the best option for themselves and the most likely outcome. In game theoretic terms, this is the Nash equilibrium, the point from which no player can improve their odds. Now, this isn't the case with the traitors, and that's because the Nash equilibrium has shifted slightly. It is still slightly better to steal since you go from 50% of the money to 100% or 0 to 0, but now one or both people stealing are Nash equilibria. If you've been stolen from, changing whether you steal or not isn't going to improve your odds. So yeah, it's still the most logical choice to steal, but you're definitely risking leaving with nothing at all. Now, the Nash equilibrium isn't the only factor affecting this. The players are, instead of the prisoner's dilemma, they're face-to-face and televised nationally. And that social pressure, on top of spending the entire rest of the game collaborating and discussing strategy, can sometimes have a stronger impact than knowing what is statistically better for yourself. It's hard to map game theory to real-life examples, especially when the rules of the game are changed, but they're a good basis point to start to understand what options are available and what might be the best move down the line. I hope you've enjoyed this series as much as I've had making it, so let me know what other Maths of breakdowns you want to see me do.